just one piece about this, typically when we do this sort of training, not necessarily the barrier assessment piece, but the second part of this presentation. It's very involved, we have a large manual pretty outdated now, but that training is usually like a full day course. So this will be like a crash course. I'm gonna be spitting a lot of information at you, quickly, so find me afterwards, chat more detail on the assessment methodologies, because it's pretty in-depth, especially certain pieces on there. But yeah, it'll be a pretty high level overview of the assessment methodology.
I'm so sorry, Dawson. Why don't you just keep going if you can?
Okay.
Try and figure out how to get
Totally.
that.
So I'm gonna cover kind of, like I said, 5 things. What is a barrier? How do we do our assessments? Associated engineering H&H modeling, so hydrologic modeling to assess those barriers. And then our water crossing assessment and geomorphology approach. Those are the five main things. But that's fine. So the main barriers that we're usually looking at, there's kind of 3 typical barriers that we usually characterize. So it's water surface drop. So difference between the outlet of your culvert, water surface elevation, and your downstream water surface elevation in the actual stream channel. And sweet, perfect. Okay. So yeah, three main types of barriers. Water surface drops, depth barriers, so depth actually in the culvert, and then velocity barriers. So those are the 3 main types. Different ways to assess all of them. There's some other types of barriers that I'll talk about in detail. There's many different ways to characterize a barrier. Okay, so these are a couple photos of these barriers.
Where's Andrea?
We'll get there.
I'm so sorry.
No worries. So the main types of barriers, like I said, 3 types. There's many more than that, aside from water surface drop velocities and depths. There's also slope barriers. So if there's excessive slope in your culvert, that can be determined as a barrier. There's rack spacing. Okay, so here you go. Slope barriers, rack spacing, what we call turbulence, aggregation or chronic debris, sediment, and then our last category is kind of professional judgment. And so we have crews at the state of Washington that do our inventory assessment crews. They do our field assessments. Different, I don't go through a couple different types of assessments that they do, but it's basically level A and level B. Level A is really they're just looking for culvert geometry pieces, and then water surface drop. Level B is more detailed. We'll get into that here in a little bit, but I just wanted to show all the different types of barriers that we can have there. A couple things to note on here. So rack spacing is there's kind of 2 things associated with that. If you have a trash rack on a culvert, there can be barriers because of sediment and debris on that. That's one thing, but there's also just a barrier in itself, depending on the spacing. So if your spacing on your racks are less than 0.8 of a feet, that's similar to our depth criteria, then that's going to be considered a barrier as well. And so when you're doing these assessments, the thing is here, it's kind of like a puzzle, try to figure out the easiest way to assess it and determine whether it's a barrier or not. You don't really should be in depth. Some of the other pieces that I want to mention, turbulence. So that's, like basically white water, really confusing to fish. They get confused and disoriented in long stretches of white water turbulence. We have ways that are outlined within the water crossing design. It's called our energy dissipation factor, and that's basically just a quantitative number to determine how turbulent your system is. There's thresholds that you want to be below based on our hydrologic design criteria. And then the last one is professional judgment. When there could be depth by just the geometry of the structure, so causing significant aggregation. There can be behavioral impediments to fish. So if your opening, maybe it's a tidal opening, is not open for long enough during migration timing, then that could be a barrier. There's also contiguous like wetted width. So if you have certain sections of your channel that are you know, you don't have it fully wetted, but there's just like little pieces all over, that can also be considered a barrier. And there's also subsurface and structural sort of barriers. And look at, you know, technical.
Hit a barrier.
Yeah, pretty barrier, exactly. All right, so methodologies, there's three main ones that I was gonna touch on. I'll breeze through the first one, second one, and third one are pretty related, and I'm gonna focus on those two. So level A barrier assessments are what our inventory and assessment crews do for DFW. They assess all state-owned culverts, primarily in the tribal junction area, border junction area. So that's Puget Sound and farther down in Chehalis Basin and north all the way up to Canada. So what they're doing there is they're really looking at just observational physical characteristics of the system. So they're measuring upstream inverts, downstream inverts, to get slopes, geometry of the culvert, and they're assessing basically slope and water surface drops. So that's really all the level A barrier assessment. It's really basic. Anybody can do it. And again, you're looking for the easiest way to determine barrier status on these crossings. Level B and engineer review, they're a little bit different. Level B is again what our inventory and assessment crews do. It's a really crude hydraulic analysis, so it's basically a single cross section, Mannings and you know, cross section evaluation. So you're just looking at backwater. You need a downstream control that you can buy that's resilient enough to determine your water surface elevation through your crossing, and you're assessing depth through the crossing and velocity. So the last one, the engineer review, is when things become a little more complicated, whether it's site constraints, access, so if there's steep slopes, or there's some hydrological complexity that our biologists maybe don't have the background, the engineering background to do that assessment. So they will kick it up to our team and can have that engineering section to do those assessments. And we can do those assessments also for not just state-owned crossings. We can help, you know, conservation districts do that sort of stuff. And we'd be happy to do that anytime. Okay, so here's the kind of main layout of a level A assessment. I'm not going to go through this in detail because there's kind of a lot here, but the big takeaway is it's relatively straightforward. You know, these are all characteristics that you can measure. You're looking at water surface drop, you're looking at countersunk, or is there natural bed in the culvert? If there's natural bed in the culvert, then depth barriers are there. You can't have a depth barrier in a natural bed culvert because it's imitating the stream. So the table on the right side of the screen, that's from our inventory and assessment manual. It's level A assessment. We're looking at water surface drop and slopes. And one thing to note there, you see the passability requirements. I don't know if anybody's done any assessment before, and come up with like a percent passability. Typically, they'll ask for that in the branch that you're doing full repair or upsizing crossing. It's really important to note that that number is purely qualitative. So when I go through and do a barrier assessment, if I hit these triggers here, this value number right there, I automatically it triggers. I just call it a barrier. And that's because those passability requirements or percentages, they're not really related to anything. They're purely qualitative, so they're like how bad is your barrier. And from an engineering standpoint, I'd like to have some and that there's conflict in the background. So it's a way for people who are prioritizing these crossings and the improvements to see how tough they are. But really, if it's a barrier, it's a barrier. It's not related to the percent of fish passing through the culvert. So it's important to note there. So level B, for all intents and purposes, we're gonna go through, we're just gonna call it an engineer review. Because you're doing a hydraulic analysis here. So the two big pieces that you need to gather for this are your hydrology and your hydraulics. So your hydrology is, there's two pieces to that here. Your high flow, your low flow. So you're looking at the worst case scenario for when a fish is migrating through your stream, through this crossing. So those are gonna be during high flow events and during low flow events, can they actually get through the structure? And then, the hydraulic piece is you're taking that hydrology, both low flow and high flows, and you're plugging it into your model or your cross-section analysis, and you're comparing that to the criteria, your depth and velocity criteria. Here is, again, another, the table from our inventory assessment manual. This all actually is, it's actually from our the Washington Administrative Code. It's in the hydraulic design section. And these are triggers based on length of the culverts. So I'm gonna dive into the hydraulic piece. This is all, like I said, it's in whack, and this is really what we have to, our teeth, for like a better term, to latch on to. When we're looking from regulatory side, does a crossing pass fish? And this is what it says. It needs to allow fish to move freely through the crossing at all flows when fish are expected to move. So that's typically, we are looking at adult fish. So it needs, we need to update guidelines for more time. That's why we push the stream simulation approach. But right now, our code is based on the swimming capability of an adult fish, and it's like an 8-inch trout is typically what you're looking at. So you need to kind of put sideboards on what this, translate this wording into what this means for both your hydraulics, or your hydrology and your hydraulics. Yeah, so your bounds are clear, and you can actually make an assessment. And so what this translates for us usually is what we say, 90% of the fish, 90% of the time. That's what your structures should be able to accommodate. And when you really dig into that, these are the two sideboards you need. Your high flow, like I mentioned earlier, and your low flow. So your high flow is the 10% exceedance flow during the time of fish migration. So that's different depending on where you are in the state, and there's many different ways to develop that. We have regression equations, fish passage, high flow regression equations for Western Washington, and then there's what we call plate factors for Eastern Washington, and I'm gonna dive into a little bit. Just to give you a taste and an overview of what we do to figure out those analyses, or to figure out those numbers. In your comparison, comparing the high flow to your velocity requirements, right? So you want to be below a certain threshold during high flows. Whereas with low flow, there's also many different ways to determine that. Often you can use a 2-year, 7-day low flow, which is from stream stats. Usually really conservative. I don't love to use that. If there's any way to do like a flow duration analysis, that's how you would develop your exceedance flows, where you're looking at actual gauge data to see how often the flows are exceeded. We would use a 95% exceedance flow. And then the other one is if you have gauge data, you can use the no flow condition, which is not actually, it's misleading in that it sounds like there wouldn't be any water in there, but it's really just there's gone out precipitation events. So it's like your base flow conditions. Yeah, so this is, I just want to cover this quickly. This is a map of Washington, obviously. These are 9 regions associated with the old USGS regression analysis that was done. This is from 1996. We're well aware this is outdated. There's been new ones that have updated. We're behind the curve. We need to update our analysis. But our fish passage high flow regression equations were developed from a regression analysis from this data set. And so in Western Washington, that's regions 1, 2, and 3. So just west of the Cascades. Regions 4 through 9, when the analysis was completed back in the early 2000s, they tried to expand it into eastern Washington, but there was no correlation between the basin characteristics and fish passage flows. So what you'll do is if you're gonna develop your high flow fish passage flows, you figure out where your site is, and then that dictates which equation you use. So here's the equations, and this is all published. If you all want this, I can share this document that walks you through the methodology. So each region has its own equation. And you're gonna see two equations there. You see the January and the May fish passage equations. So January is usually for lower elevation sites where your high flows are from rainfall dominated systems. So you're gonna get your high flows change very rapidly. So that's when the flow duration analysis was completed, and that's what these equations are developed from. For higher elevation systems, which are typically snowmelt dominated, that's when you're gonna be looking at fish passage flows. So it's important to check both of them here because you're looking for worst case scenario. So if for some reason your site is telling you, maybe you're high up elevation, but you're not above the 1,000 feet elevation, you might be on the brink of it. Check both and determine which one's worst case scenario, and that's what you would use in your hydraulic modeling. That makes sense. So it's good to check both of them. And so all these numbers and equations, these are basically just results of the regression analysis. What you need is you need your basin size in square miles. You need your 2-year, 24-hour precipitation. Usually pull that off of like isopluvial rainfall maps. And then you also need your median precipitation. And you can get most of that information from stream stats, quick analysis. You plug that in there and it's going to spit out your fish passage flows, your high flows. For Eastern Washington, again, that's for Western Washington. For Eastern Washington, we have all of these plates. There's 9 different plates. Each plate has, I don't know if you all are familiar with this, but it has really small units within it. Each unit is broken into what they call plate factor. I will show you a zoom in. So you find your site, figure out what plate it's in, then you're going to go to this next piece here. I know it's really small, I'm not expecting it to be anything, but each one of these little areas here has a different what we call plate factor, and that's the equation down at the bottom of your screen that you want. So you're taking your drainage area to your site, which is in square miles, and then the plate factor is really odd. Kind of how they develop this odd regression that they develop. The relationship is actually just drainage area. So it's a cubic feet per second per mile squared. So it's going to spit you out when you multiply that by your drainage area and your fish passage flow. And that's considered your 10% flow. So that's what you would use in Eastern Washington for high flow fish passage. And you can also check it. I usually check it with like a 2-year recurrence interval. Usually your 2 years is going to be higher. And you kind of use directional judgment on which one's going to choose to do your analysis with. Okay, so now that you have your hydrology, high flow, low flow, now you got to do your hydraulics. And the big thing here is dependent on how complex your site is. Again, you're trying to figure out the simplest way to assess this crossing. This is not for design. So you don't want to be like spending days and days on an analysis that maybe it's not even a barrier. It's kind of wasted time and money. So locate your downstream control. And what I mean by that is you need to have something downstream of your crossing. There's always something controlling your water surface elevation. So that might be like a ripple crest downstream or a log structure or another culvert downstream. And so it might also just be like stakes. And so it's important to distinguish what the downstream control is and how resilient it is. If it's just a bunch of stakes that would blow out during a high flow event, then you should really consider that's not obviously a downstream control that's going to blow out your water surface elevation. So you're going to drop and you're going to assess it as not being a barrier. Probably is. So you can figure out your downstream control and you can just run, like I said, a quick Manning's and cross-section analysis. We got one cross-section and just going through, figuring out your plugging in your flows and figuring out your water depths. So that's going to give you you have to guess and check, right, because you don't know your velocity, you don't know your depth, so you're kind of playing there. And you're figuring out what makes sense based on the end values, and then you're comparing your results, velocity and depth to, or in this case, high flow would be velocity, low flow would be depth to the criteria I mentioned earlier. And usually what I do is the sites are complicated enough, once it's got to an engineer review, that it's not just easy enough to do a simple cross section. So we're actually developing a relatively basic 1D model, and these are all steady state, pretty much uniform flow, conditions through these are always, but it's this 1D steady state model, I'm not developing a 2D model, I'm not, again, it's a pretty crude analysis. And you also want to go through and do the worst case scenario analysis, that's the big piece, is so, like I mentioned earlier, if you're downstream control, like for instance, in this picture, that was it, that the block structure going across the whole stream, it's embedded, there's another block, a tree on the other side that's kind of pulling up that log. Beavers have built on it, and this is a very beavery system in this case. We don't usually consider beaver dams as resilient structures or permanent structures. However, depending on the food availability and a lot of different biological things that they may continue to build, and then you always build your structure. If that's the case, you might assess it with a beaver dam, you might assess it without. In this case, I actually did it two different ways. One with the beaver dam and the log structure there, ran the analysis, removed it all, and used the downstream over it as a control through my structure. And then in that case, one was a barrier, one was not a barrier. So again, worst case scenario is what you're analyzing here. I'm not gonna dive too deep into the modeling, but I love modeling, so this is why I wanted to show this. It's really important to know what your model is capable of doing, and know your limitations of your model. So first you need your terrain. Your model is only as good as the terrain, the data that's put into your model. So if you use LiDAR, which you definitely can use, know that it typically doesn't pick up that imagery in the channel unless it's blown during really low flows, where it can actually pick up that imagery. So it's good to look back at like the timing of when your LiDAR was gathered, and maybe look at, if you can, look at aerial imagery to see, what was the condition in your stream. And usually LiDAR is not going to give you data, because you're not talking about a flood analysis. This is a really specific low flow sort of thing, so you need pretty high precision in your data. So usually we'll go out and do a survey. In this case, we'll do, just a simple rod level relative elevation surveys. I'm usually not tying it into actual datums, and sometimes we'll even just use a laser level. And the picture on the right, that's directly from the Heckgrass using manual. That there's 4 cross sections that you always need when you're doing sort of crossing analysis at a minimum. You need one upstream before your flow starts to contract. You need one basically right at the base of it, a little bit upstream from your crossing, one downstream at the downstream base, and then far enough downstream where your flow is fully expanded and flowing outside of your crossing. What's really tricky about this is often on these complex sites, you have multiple crossings. So sometimes in that case, you need to have a model that is assessing several crossings at once, because your flow is really never expanding fully until at the very downstream, and which is often in complicated sites like the river, so then you have backwater conditions. I'm not gonna be able to go into that, but it gets complicated fast. So again, try to simplify it as much as you can, because you have to design. The other thing, add your hydrology, both your high flow, your low flows, and then run your analysis. And another thing that I want to stress here is just that your model is as good as the data that you put into it. It's also as good as you can understand the limitations of the model. So there's always warnings, there's always notes, and there's always usually issues with a hydraulic model. It's really important to go in and try to understand what the model warnings and notes are telling you, and what the limitations that they may be providing are, and try to address them. So maybe that means going collecting more cross sections. Maybe it means going through and doing some sort of analysis where you're varying your main and values like that, but important to do that. And then lastly, you get your results and you're gonna compare it to your fish passage criteria. And so again, here's your fish passage criteria, dependent on the crossing length, you're usually looking at ranges from 4 to 2 feet per second. So you're checking the velocity and comparing it to at high fish passage, you're comparing it to that table. And then for low fish passage, you're checking the depth requirement, which is 0.8 feet. And as I mentioned earlier, if a culvert has a natural bend, and this is a little bit subjective, but you kind of use professional judgment here, but if it has a natural bed that was ideally constructed that way, like a stream simulation sort of culvert, then it can't be a low flow barrier. If there is no bed in the culvert or really fine material that's just aggraded from some sort of downstream control that's not resilient, that's when your depth barriers come into play. So important to kind of assess the sediment in your structure to understand where it's coming from and is it natural or will it flow off during a high flow event. So that's what I have for fish passages barrier assessments. I know to cover in a little bit of time, and I have a lot more for you. So if you determine that a crossing is a barrier, you're going to go through and however you find money, whatever it may be, go through and do your analysis to actually size the structure. And like I said, I know there's a lot of material, so please find me after, or hopefully I'll have a little bit of time at the end for questions. But this is going to be broad strokes. How do you do a geomorphic design analysis or assessment for a stream simulation of geomorphic design?
Yeah, that way, once your deck is like full on class, their calendar.
That's a great question. We don't have one scheduled right now, but we'll probably do, we're in the process of updating our guidelines, so it might be after that happens. But we can reach out and let everybody know this group when it happens. I think the last one we did was actually at registration. So that might be a good place to do it again. Sure.
You mentioned the flyer has got worldly capability.
Of the water that penetrates through. That's a good question. I don't know. Yeah, you can. Yeah. So if you use like penetrating liner, can get that tree. Typically, it's not penetrating that, so it's usually reflecting right off the water surface. So you know, and again, you kind of need to understand your setting and what the limitations are there and what the condition was as well.
It comes out pretty obvious in your concept.
It's just a flat line.
I figured, I'm just trying to figure out like where. When
Yeah. If they're really small streams, you know, with like more ephemeral flow, you're usually okay. But then you also get into the issue of tree cover, and sometimes that can be another issue, especially in a like low grade meadow type of grade flow system. That's you're gonna get the data there, unless it's maybe. Yeah.
Earlier on, you mentioned the percent passability and how that doesn't mean like, oh, 30% of fish are getting through. Can you say more about what that does actually indicate? So that's just a quantitative measure, like how far past the like barrier criteria something is.
It's just a qualitative, so it's kind of like how bad the barrier is the way that I mentioned.
So bigger is worse, better.
Theoretically, yeah, because I mean, you know, right, there's fish that can get through these things even at barrier conditions. That's the reality. If they're big enough, you know, they're in high flow, they might get through, but we're assessing worst case scenario. So it's, I don't have good information for you. It's based on the criteria that it showed, but again, that's not like then reference back to fish swimming abilities. So it's not saying, you know, reduction in velocity or increases in velocity by this much result in this many fish. So it's just important to note that.
But if it's this far past the depth or velocity threshold, it just gets a 33%, 66%, or
Yeah,
100%, kind of just like big.
yeah, and that's how they're probably what type of grant program. I don't even use that when I do. It's very, that's defensible, those other numbers. That's just, you know, that's the thing.
Even though those numbers are used a lot in prioritization.
Totally.
Yeah,
Planning as if it's possible, which is
Yeah.
the game, I guess.
Yeah.
Because here you say that it's. Okay, that's helpful to know.
It is gonna be. Yeah. Okay, I'm gonna jump into this next section, still quite a bit of stuff to cover here, but again, broad strokes, this is, a specific type of oversight here. There's many different types to do, many different analyses you could do, this is, you know, from our water process, the WDFW water process design guidelines, the geomorphic approach, and I'm not gonna talk about the hydraulic approach or hydraulic design criteria. So what is it? The big thing here is the geomorphic approach is you're trying to have the least effect on the natural stream processes. You're trying to continue that, the natural conveyor belt of sediment, wood, you know, changes in your channel size that naturally would occur in absence of a crossing should continue to occur with your crossing. So again, you're really focusing on continuity of your stream processes. So that's what theoretically what the geomorphic approach is. The concept behind it is a fish can get up to your structure, and you design it based on a reference reach downstream or upstream, and talk about that later, then it should be able to get through your structure because it's functioning similar to other parts of the stream. And so, like I said, it's based on that assessment of both down the adjacent reach, downstream and downstream, and also a reach assessment to determine some sort of reach. So here's the big question that you always need to ask yourself, even before you say we're gonna do the geomorphic approach. First is it suitable for the site? So do you have too much risk associated with maybe downstream sediment deposition or downstream infrastructure that you can't allow natural processes to occur? I would encourage you to always challenge that sort of thing. Maybe there's ways you can move that infrastructure away and allow for that natural processing. It's really important, obviously, to sustain the fish habitat and allow for continued processing. And then the other piece is what should it look and act like? How does the stream function and how can maybe our crossing do a similar sort of thing through the crossing? So when you're doing your analysis, you got to do a reach assessment. Where do you start? The big thing is, like I said, you try to figure out, can you use this approach? So you need to evaluate the local geomorphic indicators, metrics, conditions, and risks. An example here would be, you're looking at your adjacent approach or your reach, you're trying to make an initial assessment of can we do a geomorphic approach here? So maybe you have a old crossing that's really undersized for many decades. So it's built up lots of sediment upstream. In the meantime, development has occurred downstream, which is now would be at risk if you pull that culvert out and let things naturally go back to the pre-development conditions. So if that's the case, maybe you can get away with the design approach. So those are the types of things. It's kind of an overall site assessment based on factors outside of the crossing that you're trying to assess here. And also maybe some of the other things are, you know, do we have existing nick points in our stream that might cause head cuts that we can't have because we're trying to protect infrastructure or protect crucial habitat upstream, something like that. The other piece is that you're looking at your reference reach. And here, the question again is, what should it look and act like? Here, you're trying to determine what are the processes, what are the forms, what's the expected response, what's your channel type? Those sort of things you're determining from your reference reach, right? So your adjacent reach kind of tells you, can you do this? Will it be okay? Your reference reach, which isn't always the same as your adjacent reach, right? You might have to go to a different stream sometimes because your current stream is so degraded. But that's gonna tell you what we might be looking for to put into this crossing. So how do we actually go through this? Review this. This is a big helper. Like I said, you gotta at least do a basic assessment. I'm gonna cover super high level, basically 3 pages, and it's chapter 1 of our geomorphology design approach. So what should you be looking at? Chapter 7 is our longitudinal profile and channel adjustment, and appendix C goes through the assessment methodologies. There's many other methodologies you can use, but this is what I'm going to focus on here. So first, like I said, you're going to look at your adjacent reach, and you're looking upstream and downstream, and you need to be outside of the influences of the current structure, which sometimes is really hard to do and difficult to find. But it's usually going to have a pretty, especially if it's undersized. Usually they are if you're repairing them, upgrading them. It's going to be pretty readily apparent. You're looking to go at least 200 feet upstream and 200 feet downstream outside of the influence of your crossing. This is often what we see. Obviously in the influence area of your crossing. Undersized crossing, sediment is, your backwater is causing sediment to deposit upstream, and you have this big wedge of sediment upstream, which sometimes it'll pitch your channel down because of all that deposition, but it'll often really spread out flows. Sometimes see conditions and a branching depositional. So that's one condition that you'll see, and then in the downstream reach, this is often what we see, right? So it's all the sediment is held upstream, downstream, nothing's getting through, so it continues to just erode and size downstream because sediment is not coming through. So sediment start downstream, sediment rich upstream. And so you want to be outside of these influences. Sometimes they can go pretty far depending on the scale of your stream. So then we're going to look at a reference reach. And I don't know that I'm going to have to lead through all of these things, but these are the 5 metrics that you really should be focusing on when you go out to your site. Some of these require more computer development, computer work, or like desktop analyses, specifically the long profile and your expected regrade. But a lot of them you just find plenty of help on the site. So the first one is obviously your bankable width. Your bankable width is for the most part, usually what is used to size the width of your crossing. It's the point where your stream begins to get out of the banks, like in size. The indicators are different. Different sites, sometimes it's really hard if your site is really confined. Bankable width is very difficult to determine because it's steep walls, so you're not really going to have much vegetation change because of all the erosion. But usually there's kind of a slope break between your actual active channel and your floodplains, or like a significant change in vegetation. That's kind of what you're looking for there. Usually you want to measure it in a place that's pretty uniform, so pretty straight. Bends are usually going to expand your channel. You want pretty natural reaches. You don't want to be taking bankable width measurements in a channel that is really confined or actively eroding. And you're looking for those well-defined indicators. And the other thing is where you're putting your crossing and where you're taking your bankable width measurements in your reference region they should be similar, sort of slope and confinement, right? Because if they're not, you're going to be designing for something that's not going to be sustainable. It's just going to change over time. Which geomorphology approach should be okay, right? Because we're allowing the stream to do what it needs to do to adjust to our mistakes as engineers. So places to not measure it, don't measure it in a place like that. You know, with the, you know, big, large wood accumulation, awesome, but probably not gonna be indicative of your reach, especially if it's for confined, maybe if it's completely unconfined. Might be a really great spot, but it's probably gonna tell you widths that are much larger than what your crossing site should be. Again, don't do it at bends. Typically you don't wanna do it in really incised places where there's exposed bedrock, you know, or clay or hard materials. Okay, flood prone width. This is another measurement you're gonna be taking. It can be determined in the field. It's kind of difficult. It's kind of like your high flow indicators, but typically the way that there's two different ways to determine. It's either 2 times your bankable depth. So once you figure out your bankable width, measure that channel depth at that width, and then basically double that, get your stadia go up double, take a right. That's one way to figure out for your flood prone width. The other way is to develop model. So your flood prone width is your water surface elevation. Makes sense. Unless you feel like your model is. But maybe try first. So that's how you're gonna determine those. And it's using the floodplain utilization ratio. This is important because this kind of tells you you're within the geomorphic design approach. This is gonna tell you, do you use your standard bankable width equations, or do you use a different approach? Which would be like our confined bridge approach. And I'm not gonna, unfortunately, don't have time to go into detail into what that is, but this is how you would distinguish it. You're taking your flood prone width over your bankable width, and if it's over 3, you consider that to be unconfined. It's not really that unconfined, but we consider it unconfined. So here's some examples. Confined is basically, you know, your really steep transport reaches that are confined between, you know, bedrock walls, and your bankable width is the same as your flood prone width. It's just going up, it's not going out. Whereas unconfined is usually lower gradient. You have really wide valley walls, and often frequent overlay floods. Moderately confined, roughly around 2, somewhere between 1 and 3. That's a lot of most of the systems that we deal with. But it is important to make note here is when you're doing this analysis, is the current condition a result of degradation that you can maybe help reverse through another restoration project, combined with your crossing replacement, or is this naturally just a system? Is most of our systems are incised and entrenched and give you results of flood utilization ratios that are usually less than 3. Okay, so this might be the only one, see what I can get through, but this is a big one here, long profile adjustment. I would say this one will really determine the long-term success of your crossing. And it's associated with the bottom 2 as well, but you need it. It's also really subjective and difficult to determine, because you're trying to look for your the natural prevailing equilibrium slope in your entire, basically through your whole reach, not just your crossing, but containing your crossing and beyond. So again, this is another place where you're kind of asking yourself, can you get away with utilizing the geomorphic approach? Because if your crossing is gonna have to be over steepened because of grade breaks, then maybe it's not gonna work there. This is an example of what you would be looking at for a long profile adjustment kind of analysis. So you're looking at, like I said, this is over a mile. So this is often pulled from LiDAR, with additional survey that's brought into it. The crossing is here. And so you're looking at what are the downstream controls that if, you know, a head cut was to move through, or, you know, there's some midpoint or something that can significantly change our bed elevations, what would that do to our crossing? And that's gonna kind of tell you, maybe a little bit about your sediment that you're gonna put in there and also the depth of bed, embedment or countersinking, or potentially even like related to your shower protection and footings. So you kind of, you want to look at both, what's the possible degradation? So what happens if head cut comes through? Or what happens if, you know, if our crossing is currently degraded and lower than the natural equilibrium slope, it may grade. So do we have enough headroom to clear that debris and that sediment that's coming through? That's a really big important piece in this analysis. And again, like I said, it's difficult to determine. It's pretty subjective, right? If you change any one of these starting points where you're measuring your slope, it's gonna change the difference between your design bed elevation and your potential long-term profile adjustment. Sediment gradation, another piece that you want to be looking out for at the site. This is ideally your sediment gradation in your reference reach should when you determine what that is, that basically should be what you're putting in your crossing, which is the same material for, you know, for high gradient streams. Often that's a lot more larger material that's not mobilized very often, except during really high flow beds. For lower gradient systems, that bed is going to be like moving through pretty often. And that relates to the last piece, which the sediments apply. So you have to be careful there. If you put in a fine grained bed and you have a lot of degradation upstream or sediment sinks upstream, you're not going to get the sediment to replenish your culvert. So maybe in that case, you need some things would put in some things to hold in the sediment, right? So this should be you quantify the sediments in order to serve as your basis of design for your structure. Usually what we do is we do a Bowman pebble count, where you're going through and you're picking up rocks, pebbles, sediment in the stream, and you're recording it. I usually do at least 4 pebble counts for a stream crossing. In each one, I'm getting 100 pebble pieces of sediment, and then you can go through and develop your sediment gradation curve. One thing I wanted to note here that I've seen recently, which has kind of caused some issues and from the regulatory side, is if you have a system that's relatively degraded, maybe from sediment being stored upstream, and so it's really bony downstream with bigger boulders. A little hard to conceptualize, but you can have bias in your pebble count. So think about like if I go and I'm walking through my stream and I touch a big boulder on the ground, that takes up a lot of space, right? A lot of volume. Whereas if I go through, there's a lot more smaller pieces of material. So that would have to be in place to make up one big piece, right? So one boulder that's a cubic meter would require, you know, 100 cubic centimeters, little guys, if that makes sense. So then when you transition from your pebble count to your sediment gradation, which you utilize to size your sediment, it's going to show that you have a lot more finer material, right? Because you're taking number of quantities to volumetric gradations. It's a little hard to conceptualize, but the reason why I bring that up is because in those higher gradient systems that are maybe more bony, your sediment gradation from your pebble count might tell you that you need, and it's significantly finer than what you actually see out there. So it's a little, going back and forth between pebble count and volumetric gradations is sometimes a little difficult to see, and it can be biased towards to smaller materials actually. Okay, last thing, I know I'm out of time, but real quick on this sediment supply, and I mentioned it earlier, you should be thinking about this when you're thinking about doing a geomorphic design approach. It relies on sediment transport and deposition. So if you don't have sediment to replenish what's in your structure that you're placing there, it can blow out, and now you just have well, maybe you have scour protection material and bony riprap, or you have the bed of your actual crossing. So it's important to know what's going on upstream and how that might influence the bed characteristics of your culvert over time. The other thing is, understanding where you are within, your kind of sediment regimes of the entire watershed. Are you higher up, or are you in a location downstream where you're expecting deposition? Or are you expecting more to be transport? And that's also related, to your morphology of your streams. So higher gradient, step pool, or rigid and stable bed, right? So I mentioned earlier, your lower gradients are gonna be more mobile bed, maybe wood force steps if you have steps. And these are some indicators of what you might see upstream, that might tell you, should give you a little bit of pause as far as, are you gonna have enough sediment coming through your system to supply? If you have significant incision and bedrock upstream, it's probably not gonna be, there's probably not gonna be a lot of sediment. Sure. Or maybe there is, and it's just, it needs to be held up in your beds, you need something to kind of create that channel. All other things are, sediment leaks, beaver ponds, wetlands, lakes, those sort of things. Upstream. Real quick, takeaways from this, the big thing is here, in your barrier assessments, as I wrap up here, just try to figure out the simplest way to do it. If any piece through your analysis tells you in any part downstream, within the influence of your forward complex, tells you that it's a barrier, then the whole thing is a barrier. So look for those site indicators and try to relate them back to actual data. And also I would say trust your intuition. Like you see major scour downstream, it's probably an indicator that you have really high velocities. Might be, go with your gut, check that first if you're doing your analysis rather than through both low and high flow. And then, reach out to us if you have like a complex site or you want to talk more in detail. I'd be happy to talk through this, or I'm sure anybody on our team as well. And lastly, here's some takeaways for design. Geomorphic design approach is all about the continuity of stream processes. So that's what you're aiming for when you design your processing. Like I said, more detail in the water crossing design guidelines about your long profile and your potential edge up adjustments. I would say it's really important to do your best on that, and hopefully you get it right, and if not, give your structure wide enough space and enough bed elevation to make the adjustments it needs to itself. And the last thing, and I didn't talk about construction at all, but obviously you gotta have good drawings and you really need good construction inspections, because if you don't have inspections to go with your drawings, they're kind of. That's what I got.
Thank you, Dawson. I think we've had